Tes. Udah, ada yang nonton.
In the previous chapters, the models had one numeric and one categorical explanatory variable. Let's see what changes if you have two numeric explanatory variables instead. Two numeric explanatory variables plus a numeric response variable gives three numeric variables to plot. Since scatter plots are designed to show relationships between two numeric variables, it takes more thinking about. There are two common choices. Either we draw a 3D scatterplot or a 2D scatterplot using color for the response variable. Let's revisit the fish dataset, which now has an extra numeric column, the height of the fish in centimeters. There are multiple options for drawing a 3D plot using Python, but this is beyond the scope of this course. The main issue here is that the plot is impossible to interpret. The fundamental problem is that screens are two-dimensional, so 3D plots always suffer perspective issues. The only way to circumvent this is to create an interactive plot that the audience can rotate to explore the data from different angles. Maybe virtual reality will also be useful to solve this one day, but for now let's move on to the next type of plot. The next plot type to explore uses color for the response variable. This is a standard 2D scatterplot, so we can use Seaborn, setting the U argument to mask G. Interpretation-wise, it is an improvement over the 3D scatterplot. As you move up and to the right of the plot, the colors get darker, representing heavier fish. Modeling with an extra explanatory variable isn't much different than what we've seen previously. The explanatory variables on the right of the formula are separated with a plus, as before. You get a global intercept coefficient and one slope coefficient for each explanatory variable. The prediction flow is no different. Create a data frame of explanatory values with product from itertools, then add a column of predictions with the sign and predict. The plotting code also remains largely the same. I create two scatterplots, one with the actual data points and one with the prediction data points. To avoid duplication, the legend in one of the scatterplot calls can be removed. For clarity, I also changed the prediction data point markers to squares with the marker argument. The results look like this. The color grid gives a nice overview of how the response variable changes over the plane of the explanatory variables. The heaviest fish are in the top right, where they are long and tall. To include an interaction in the model, the only change is to replace the plus in the formula with a times. This gives you one extra slope term for the effect of the interaction between the two explanatory variables. The prediction flow is exactly the same as before, repetitive but pleasingly easy. The only thing that has changed is the name of the model. The plotting code is identical, but the colors on the plot are slightly different. In this case, the colors of the square predicted points closely match the colors of the nearby circular data points, which is a nice visual indicator that the model is a good fit. Time to apply all this on the housing dataset.
Lagi kuliah kamu, Ibu? Hah? Lagi kuliah apa ini?
Apa? Kuliah nyelesain course.
Wih, live itu.
Iya.
Hah?
Iya. Hah? Gak ada yang nonton.
Wah, kamu lagi live emang?
Heeh.
Ya udah.
Ben nggak langsung scroll HP maning.
Sarungnya sering kembang-kembang sih.
Aneh-aneh. ke makin terang makin mahal. SRT distu LRGM. Oh, yang terus dari meski convenience number instead of 10 arrows 110 product and dari wait. Exploratory data. Invalid syntax. Wait. Duh. Valid syntax. PD dot. Mana sih? Oh, nggak pakai ini ya? Iya. Sekitar after noise. And convenience. Ini adalah ada marker S. Change the name of model. Maksudnya sama kan? Check the recall of OLS redo specify formula times terus this enter this
Regression models aren't limited to two explanatory variables. Here, we'll consider 3 of them and think about what happens when you increase that number even further. In the last video, you saw this scatter plot with the response variable mass indicated by color and the explanatory variables shown on the x and y axis. You can see several distinct clusters of points. Perhaps these correspond to the different species of fish. We can check this by faceting on species. You can give each species its own panel with the facet grid function from Seaborn. In the first step, you prepare the grid by specifying the layout. The call argument allows you to split by species, and the call_wrap argument makes it a 2x2 grid. The palette argument can be added optionally to improve the coloring. The second step is to map what visualization you want to plot on the grid. In this case, you specify a scatter plot with length and height on the x and y axis respectively. There is a noticeable strong positive correlation between length and height for each species of fish. The relationship between the explanatory variables and the response is harder to quantify because you can't determine colors as accurately as x and y coordinates. In this example, brighter colors mean heavier fish, so for each species you can see that as fish get longer and taller, they also get heavier. In general, while it is tricky to include more than 3 numeric variables in a scatter plot, you can include as many categorical variables as you like using faceting. However, more facets can make it harder to see an overall picture. Plotting rapidly becomes more challenging as you increase the number of variables to display. By contrast, modeling doesn't get much harder as you increase the number of explanatory variables. Here, there are 3 explanatory variables and the only change is that you include an extra plus. The main tricky thing about including more explanatory variables in models is that there are more options regarding interactions. This model specifies no interactions between variables. You could also include two-way or pairwise interactions between the explanatory variables. A third option is to include a 3-way interaction between all the explanatory variables. This syntax quickly becomes cumbersome to type, so fortunately there are shortcuts. You've already seen the concise syntax for including all the interactions. Simply swap the plus operators for time symbols. Both these formulas mean the same thing. You still need a plus before the 0 to denote not including a global intercept term. To get only 2-way interactions in the model, but not the 3-way interaction, you can use a new syntax, namely wrapping the explanatory variables in parentheses and raising them to the power of 2 with 2 asterisks. The prediction flow with an extra variable contains no surprises. This builds upon what you've seen before. Product can easily take additional arrays as arguments. Modeling code scales nicely with more variables. Notice, however, how rapidly the dimensions of the prediction dataset increase to account for all combinations. Visualizing these predictions isn't as useful anymore since it reaches the limit of visual interpretation, so we stick with predicting the response variable instead. Time for you to make some models.
Asam, apa namanya? Grid plot. Facet grid. X-axisnya N, Venus Y-nya list M harusnya nggak perlu nggak sih, udah di sana. Coba. Bahasa sintaksnya. Oh. Terbuat. Kok malah SQRT-nya yang di x-axis? Semua three-way inter. Boleh pakai kali kan harusnya. Terus SI two-way interaction itu yang ini kan pakai titik dua. Oh, boleh pakai ini. Kok kuadrat Pismo seperti itu. S plus The column assigning prediction data. Coba assign nama price data.
Let's see how linear regression works. To keep things understandable, we'll stick to simple linear regression with a single numeric explanatory variable. Here is the standard scatterplot of a simple linear regression. Here's the same plot, showing the residuals, that is, the actual response minus the predicted response. For the best fit, we want those red lines to be as short as possible. That is, we want a metric that measures the size of all the residuals, and we want to make that as small as possible. The simplest idea for that metric would be to add up all the residuals. This doesn't work, because some residuals are negative, so they would make the total smaller instead of larger.
Absolute.
Instead, we do the next easiest thing, which is to square each residual so that they are non-negative and then add them up. This metric is called the sum of squares. The tricky part is determining which intercept and slope coefficients will result in the smallest sum of squares. To solve this problem, we need to take a detour into numerical optimization, which means finding the minimum point of a function. Consider this quadratic equation. The y value is x squared minus x plus 10. The plot shows that the minimum point of the function occurs when x is a little above 0 and y is a little below 10. But how can we find it exactly? It's possible to solve this with calculus. Don't worry if this doesn't make sense, you won't need it for the exercises. You find the minimum by taking the derivative, setting that derivative to 0, rearranging for x, then substituting back into the original equation to find y. It gets the right answer. X is 0.5 and y is 9.75. However, not all equations can be solved in this analytic fashion. And ever since Newton and Leibniz invented calculus, mathematicians have been trying to find ways of avoiding it. In fact, one of the perks of being a data scientist is that you can just let Python figure out how to find the minimum. To perform numerical optimization in Python, you can use the optimize package from SciPy. In this case, you'll need the minimize function. The function you want to minimize is defined here. It takes x as an input and returns y as x squared minus x plus 10. Then you call minimize. The first argument is the function to call without parentheses. The second argument is an initial guess at the answer. For more complicated functions, this is sometimes important, but here you could pick anything. In the output, you see fun, the estimated y value of the function, which is spot on. The x value is at the bottom. It's close to the correct answer of 0.5, and if you need better accuracy, there are many options you can play with to improve the answer. The other pieces of output are diagnostic values, which we don't need here. While OLS is hundreds of lines of code, you can implement simple linear regression for a specific dataset in just a few lines. You define a function that accepts the intercept and slope and returns the sum of the squares of residuals. You'll have to use the trick of giving the function a single coefs argument, then extracting the individual intercept and slope. You'll perform the rest of the calculation yourself in the exercises. Then you call minimize, passing an initial guess for the coefficient and your sum of squares function. That's it. Time to delve into linear regression's internals.
Semakin jauh errornya semakin tinggi. Of course. Koefisien intercept sama slope adalah intercept plus slope kali harusnya x nya, tapi apa x aktual difference aktif ada kok sama guys. Information 8,224 cm sama. Oke, 1 chapter setengah jam ternyata guys.
In this last chapter, let's switch from linear regression to logistic regression. We'll revisit the 3-column bank churn dataset from the previous course. Has churned is the response, denoting whether or not the customer churned. Time since first purchase is a measure of the length of relationship with the customer, and time since last purchase is a measure of the recency of activity of the customer. The explanatory variables have been transformed to protect commercially sensitive information. Recall that to perform a logistic regression in stats models, you use the logit function instead of OLS. To extend logistic regression to multiple explanatory variables, you change the formula in the same way as linear regression, with a plus to ignore interactions or a times to include interactions. There's no new syntax here. Recall that when the response variable has 2 possible values, there are 4 outcomes for the model. Either it correctly predicts positive and negative responses, or it gets it wrong with a false positive or false negative. We can quantify and visualize these 4 outcomes using a confusion matrix. The code for calling the prediction matrix is shown here, as we saw in the previous course. The confusion matrix lets you calculate metrics like model accuracy, sensitivity, and specificity. You will do this in the exercises. The prediction flow of multiple logistic regression should also feel familiar, since you've seen all the techniques already. Use iteratool's product function to create combinations of explanatory variables, store them in a data frame, then assign a new column of predictions. For visualization purposes, I also create a column with most likely outcomes. It holds the rounded values of the churn predictions. If the probability of churn
Datacamp.
is less than 0.5, create a column of predictions.
Skip this. Ini bikin biasa.
For visualization purposes, I also create a column with most likely outcomes. It holds the rounded values of the churn predictions. If the probability of churning is less than 0.5, the most likely outcome is that they won't churn. If the probability is greater than 0.5, it's more likely that they will churn. Then, 2 scatter plots are drawn, one for the actual churn data and one for the prediction data, colored by most likely outcome. You'll see what it looks like in the exercises. So go ahead and get started.
Wih, yang nonton di kafe, halo Zakiuddin. From stats API or get fit logistic. Ini sudah pakai get ya. Get. Churn status vs length of relationship. Has churn interaction between tidak pakai enggak dibilang ini sih Ini kali ya.
Aku sigma EZ core X. Wih, buset.
Great time. Sequence from -1 ke 6. Stepnya -1 sama 6,1 produk frame P kolom apa iki? Your sequence start at -2 from -2. Wah, salah baca. To 6. Oh, -2 sampai 4, -1 sampai 6. Betul kok. Namanya harusnya model ya Jun is put in edit data turun prediction data has Jun mesin Jun presensi konsum status wait pakai apa plotnya bebas udah scatter plot
Respect. Wih,
halo Bimo sip Y-nya adalah versi ini Jun data Jun data nya time since purchase ini di kompas Presensi of process. Oh, Peang. Halo Kebumen. Wih, halo Jogja. Oh, ini color powder. Oh, kebalik. Ini sudah. Gede gambarnya. Nah. Wow. Using certain dataset. Oke, maaf. Ini gimana gambarnya? Wow. Using prediction data. Harusnya sekarang. Begini. Sama kupas aja. Prediction data. Gue-nya most likely outcome yet. Wow. MDL certain vs inter dot conf dot apa table gitu, bread table. Negatif terus positif, matrix negatif terus positif, satu false negatif terus positif neutral 1, terus konteks 0, akurasi adalah kebalikah. Ini kok data extract the element second row. Nggak gini ya aksesnya ya, bodoh juga gue. Gini ya. Harusnya sama nggak sih? False negatif itu yang 1,0 kali TN plus TP TN FM FP harus dong.
In order to understand logistic regression, you need to know about the logistic distribution. Before we get to the logistic distribution, let's look at the Gaussian or normal distribution. Hopefully, you are familiar with the famous bell curve of its probability density function made with SciPy's norm.pdf.
Norm.pdf.
Function. For the purposes of regression, we care more about the area under this curve. By integrating the norm.pdf function, calculating the area underneath it, we get another curve, known as the cumulative distribution function. To get the cumulative distribution function, or CDF, you call norm.cdf instead of PDF. The y-axis is near 0 on the far left of the plot and near 1 on the far right of the plot. This is a feature of the CDF curve for all distributions. When x has its minimum possible value, in this case minus infinity, y will be 0. When x has its maximum possible value, in this case infinity, y will be 1. You can think of the CDF as a transformation from the values of x to probabilities. When x is 1, the CDF curve is at 0.84. That means that for a normally distributed variable x, the probability that x is less than 1 is 84%. Since the CDF transforms from x values to probabilities, you also need a way to get back from probabilities to x values. This is the inverse CDF, also known as percent point function, PPF, or quantile function. Here we have a new data set with probabilities from nearly 0 to nearly 1. The inverse CDF is calculated with norm.ppf. The line plot you see is the same as the CDF plot from the previous slide, but with the x and y axis flipped. Here's the logistic probability density function. Here's the logistic probability density function. It looks a little bit like the Gaussian PDF, but the tails at the extreme left and right of the plot are fatter. The CDF for the logistic distribution is also known as the logistic function. The two terms are interchangeable. It has a fairly simple equation, 1 divided by 1 plus e to the minus x. The inverse CDF is sometimes called the logit function. Again, the terms are interchangeable. This may ring a bell. Recall from the previous course that logit is also known as the log-odds ratio for describing predictions. Its equation is a logarithm of p divided by 1 minus p. In order to see what these curves look like, you'll have to try the exercises. Let's have a look at those curves.
From say by from -10 to 10 minus 1 terus X CDF Create the data frame restart kalau nge-lag. Refresh maksudnya. CDF man Anderson Files manually transfer to information CDF sama dengan manual 2 plus X wait ini ya kayaknya ya tuh oh iya betul ada please plot look CDF SX dot ini pakai line plot line plot sintaksnya betul X data statistik salah preparing from login logistik is logistik.php ya, ppf x look dari paper sekian stop and plot ini adalah login apa sih, data logistik distance inverse. Lihat dulu, wow, dikit lagi tamat, 1 jam doang ternyata. The logistic serious changes to the parameters and the of course. Ini kayak gini nggak sih? Bikin ya. No. Hai. As location increase, the logistics area record as scale increase, sections slope increase. Enggak. Scale increase, slope-nya turun. Decreases. Okay guys, tinggal video.
Let's see how logistic regression works. The principle is the same as for linear regression. Choose a metric that measures how far the predicted responses are from the actual responses and optimize that metric. In the linear regression case, the metric to optimize was a sum of squares. That is, you can
Boy kalau pecah 7 terus anggap 7 course yang benar-benar kebunuh ilmunya enggak. Menarik. Bisa. Wait. Boy berarti 8 enggak sih? 7 itu yang elemen-elemen pecah, tambah 1 yang elemen gabung semua. Nah, biar tugasnya sama, boy yang 1 nggarap course 8, terus yang pecah 7 nggarap course-nya masing-masing. Terus pas jadi 1 otomatis dapat semua kan? Ya gitu, harusnya.
calculated each predicted response minus the corresponding actual response, squared it, and took the sum. In the case of logistic regression, the actual response is always either 0 or 1, and the predicted response is between these two values. It turns out that the sum of squares metric optimizes poorly under these restrictions, and that there is a better metric. This is the likelihood metric. Unlike the sum of squares, where the goal was to find the minimum possible value, with likelihood you want to find the maximum value. You take the product of the predicted and actual responses, and add the product of 1 minus the predicted responses and 1 minus the actual responses. Then you sum overall data points. Since the actual response only has 2 possible values, this equation simplifies in 2 different ways. When the actual response is 1, the equation for each observation simplifies to the predicted response y-pred. As y-pred increases, the metric increases too, and the maximum likelihood occurs when y-pred is 1, the same as the actual value. When the actual response is 0, the equation simplifies to 1 minus the predicted response. As y-pred decreases, the metric increases, and the maximum likelihood occurs when y-pred is 0. In either case, you get a higher likelihood score when the predicted response is close to the actual response. When calculating the likelihood, y-pred is often close to 0 or 1, which means you end up adding up lots of very small numbers, which introduces numerical error. It is more efficient to compute the log likelihood. The only difference in this equation is that you take the logarithm of the predicted response terms. Optimizing to find the log likelihood gives the same coefficients as optimizing to find the likelihood. Since we want to maximize likelihood, but the optimized package can only minimize functions, one tweak to make is to calculate the negative log likelihood. That is, include a minus sign when you calculate the sum of each observation's likelihood contribution. Now we are set to write our logistic regression algorithm. The metric function takes a coefficients argument, you extract the intercept and slope from it, and perform some more calculation that you'll see in the exercises. From SciPy's optimized package, you'll then use the minimize function to find the coefficients that minimize the metric. Almost there.
Almost there. Oh, itu terakhir. As you get closer and best fit to look likelihood. Harusnya buat likelihood ini apa? Intercept di sekitar situ slope-nya semakin slope-nya mendekati ini turun sama ini turun. Satu. Oh, ini naik ke likelihood, naik log likelihood turun. Oops. Buat maksimum lah, bodoh. Kok unpack inter slope calculate prediction intercept plus slope kali itu udah sih. Oh. Look, you bread, actual plus look something you bread, something ya atur kok atur lah Statistika. Hop. Woi, congratulations.
Well done! You've learned multiple linear and logistic regression. In Chapter 1, you fitted, visualized, predicted and assessed parallel slopes linear regression models. In Chapter 2, you explored interactions between explanatory variables and tried to resolve Simpson's paradox. In Chapter 3, you saw that although visualization gets tricky with more explanatory variables, modeling easily handles them. In Chapter 4, you ran logistic regression with multiple explanatory variables and explored the logistic distribution. On top of that, you implemented algorithms for linear regression and logistic regression. That's a really advanced thing, so well done! In order to master regression, there are a few more things to learn that we didn't have time for in this course. Firstly, it is common practice to split your data into separate training and testing datasets. You calculate the model coefficients on the training set, then assess the performance of the model on the testing set. This helps prevent overfitting, where your model only works well for one specific dataset. Secondly, an even stronger remedy against overfitting is to use cross-validation. This involves fitting and assessing the model several times against several random training testing splits to give a set of models from which to choose. Thirdly, in order to help determine which explanatory variables should be included in the model, linear and logistic regression return the significance of each coefficient, which is a measure of whether the coefficient is really different from zero or it just appears to be different from zero by chance. Datacamp has many more courses on advanced regression techniques. You're now ready to take them. Congratulations again!
Tamat. Intermediate regression. Kelas King, yoi. Kita lihat leaderboard. Tetap yang paling ya dari XP earn ya. Aku 8450. Kalau sama dilihat dari apa? Kok aku masih 7 ya? Refresh. Kamu aku masih 7. 8450 itu. Clear kan? Completed. Nah udah 58. Yaudah segitu aja sih guys. Udah ya, tamat ya.